Today we're going to be looking at a heavily requested channel, B1M. Specifically, why these Soviet-era nuclear reactors are being taken apart. Well, they're old. For those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
What happens when a giant nuclear reactor comes to the end of its life? More than half of these hugely complex systems are now over 30 years old, and many have already been running for longer than they were supposed to.
So 30 years old, at least for plants that are built in the US, not really that long. A license for a nuclear plant in the US is typically 40 years. And many of them, including the plant that I worked at, have received license extensions for another 20 years. And that is a very involved process. There's a lot of engineering and design analysis and system upgrades that need to be done to extend your license. So that's a very expensive process, but nothing compared to building a brand new nuclear power plant or even decommissioning. Decommissioning can get very expensive. And there's even ideas out there of getting a second license extension to 80 years. So at least within the US, 30 years is really not that old.
The answer sounds simple at first. You take it apart. But how do you dismantle something this big and hazardous, and why are some projects taking decades to complete? Well, let's take a look inside one power plant that sets a new standard for nuclear decommissioning to see how it's done. If you thought nuclear power was mostly a thing of the past, think again.
Ooh, I'd certainly hope not. But no, nuclear power is still widely used around the world. New nuclear plants are still being built, not as quickly as they used to back in the 1970s, and I was glad to see 2 new reactors built in the US very recently. That's Vogtle Units 3 and 4 in Georgia. I definitely do not see it as a thing of the past.
Right now, there are more than 400 active nuclear reactors worldwide, and that number could grow significantly. It's a type of energy that's now considered much cleaner than fossil fuels when combined with renewables, even when you factor in the waste.
It is a lot cleaner than fossil fuels. He mentions when combined with renewables, so at least the plant I worked at did not incorporate renewables. It wasn't part of a company that did renewables as well. Now, there are companies that do both nuclear energy and renewables, such as wind and solar, but what nuclear does that renewables don't is supply baseload energy to replace things like coal. Whereas renewables, while they have made great strides in recent years, still doesn't produce the magnitude nor the energy stored required to fully replace coal by itself. I'm not saying we shouldn't have renewables. I'm just saying nuclear doesn't need renewables to replace coal.
Why there's been a drive to build more power plants and maintain the ones we've got. But therein lies the problem. By 2050, almost 50% of the reactors currently in use worldwide are set to begin decommissioning.
50% scheduled to be decommissioning by 2050. I mean, that would bring up the age a lot. So you would have to do a massive amount of license extensions and essentially refurbishment projects rather than being decommissioned. But I've seen stats that were showing similar numbers by 2030, even 2020, which is already long since passed. So it's not that 50% number. I would take that with a grain of salt. Just because it's on schedule doesn't mean it's actually going to happen, especially when you're looking out 20, 25 plus years.
Brief terms, decommissioning is the process of dismantling a nuclear reactor or facility when it's no longer needed. It involves removing the fuel, breaking down the various structures and components, extracting all the hazardous materials, and doing lots of decontamination.
So there's a lot involved in decommissioning, and full disclosure, I've never been part of a decommissioning project. They're quite rare, and there's probably only a handful of people that have, even within the industry, that have ever actually done it since, like I said, licenses last 40 years at a minimum. There have been post-accident decommissions, such as in 3 Mile Island or in Fermi Unit 1, and there's been several, but a lot of it isn't recent history, at least within the US. So it'll be interesting to see if we were to start decommissioning on a large scale and hopefully replacing them with modern nuclear reactor designs rather than abandoning things altogether. But it would be good just so to at least gain some practice or at least more familiar with the process. We saw this when Vogtle Unit 3 and 4 were built. There were so many slowdowns and lessons learned just because there's been such a gap within the US of building nuclear power plants. So it would be interesting. It's just another one of those things that since it hasn't been done recently very much, people just don't know how to do it.
Afterwards, the site can either be used to put new reactors in, or for something else entirely.
That's true.
Why would a reactor be decommissioned? Well, it could be down to new regulations, running costs, or maybe it's in a country that's decided to phase out nuclear completely.
That right there is very sad. It just really is.
Like Germany or Italy. But this power plant elsewhere in Europe is being decommissioned for a different reason.
So there's a lot of steps involved in decommissioning, at least. One, just like anything else, you need a plan that requires regulatory approval within the nuclear industry. You shut down the reactor, and you offload all of the fuel. You place it in the spent fuel pool, and then when it's decayed enough, you transition that into dry cask storage for the long term. You do a detailed radiological survey to assess radiation levels and contamination levels, and that tells you what you need to clean up. So you're going to decontaminate a lot of surfaces and equipment, such as the reactor coolant system. You formulate a plan for safe storage of your radioactive waste. Again, the most hazardous is the spent fuel itself, but we'd also need a plan for your lower and intermediate level waste, which isn't nearly as involved. You're not working with timelines that would have to span decades or even centuries for this stuff because it just doesn't last as long, but you still need a plan for it. Probably transport it to a satellite site for ones that, and that's going to involve coordination with departments of transportation to make sure everything is labeled safe and stored safely according with regulatory requirements. You're going to need to remediate the site itself, the soil, the groundwater, any cleanup, and then do a final radiological survey to ensure it's consistent with site release criteria. So and that's just the radiological aspect. There's other things with other sorts of hazardous material that you would see when you decommission hazardous chemicals, for instance. You'd see the same sort of stuff when you decommission a chemical plant. Though at a nuclear plant, it's not nearly as much of a concern, mainly because you just don't use as much compared to, say, a petrochemical plant.
Slovakia joined the European Union in 2004, it did so under one key condition. Formerly parts of the Union in 2004, it did so under one key condition. Formerly parts of the USSR, it would have to take apart all of the Soviet-era reactors it still had in operation, which no longer met the EU's safety standards.
So yes, Soviet-era reactors, I'm sure most of you have heard of Chernobyl. Infamous poor safety standards. Not a true reactor containment building to prevent a radiological release. Infamously bad control rods with graphite at the tip. And control rods are the brakes for your reactor, so this was the equivalent. And graphite is a moderator, which slows down neutrons, increasing the chances of causing fission. So graphite tipped control rods is basically if you slam on your brakes, you actually accelerate for a split second before you brake. And a whole bunch of other poor design details that I discussed in my Chernobyl videos. Now, a lot of those design features were improved after Chernobyl, such as those control rods, for instance. However, by today's standards, by European and American standards, it's still not. A lot of older reactors still don't meet those standards. So can totally understand why those are being commissioned.
A pair of reactors at the V1 nuclear power plant in Bohunice, which had been running since 1978, were unfortunately on the list. They were among the first WWER reactors, a type of pressurized water design to come out of the Soviet Union.
So WWER reactors, I've also seen it as VVER reactors. They're types of pressurized water reactors, so think of a precursor to, say, a Westinghouse 4-loop pressurized water reactor like the plant I worked in. water cooled and moderated, so they're not graphite moderated like Chernobyl. They have a pressure vessel, so they're highly pressurized. They do not boil. Like Chernobyl was actually a type of boiling water reactor. It was a very weird boiling water reactor, but it's a completely different category. But it's still old. Some older designs, like the WWER 440, I mean, they only had a power output of 440 megawatts electric compared to the WWER 1000, which had 1,000 megawatts electric. So, which is a bit more closer to what you would expect for a nuclear power plant to put on the grid. But some of the older designs, again, didn't have as robust containment structures, at least compared to Westinghouse pressurized water reactors. Less strict criteria for their emergency core cooling system in terms of how many safety trains of emergency core cooling system you have. That is to say, how many pumps you have that can run in parallel so that even if one fails, you're still good from a nuclear safety standpoint. Less robust seismic standards, and newer reactor designs such as the AP1000 include more passive safety features that rely on forces like gravity and convection, which do not require electrical power to operate. So yeah, they're just older. I think they're safer than Chernobyl, but they're still just older and not as safe if you look at the core damage frequency metric, which is a probabilistic risk assessment tool used to assess the safety of nuclear power plants. I commonly use this when you take equipment out of service for maintenance. It runs probability models to say, hey, with one less safety-related coolant pump, odds of core damage go up by this much. And it's still pretty low. To give you a sense of scale, core damage, so not even a radiological release, but core damage, say a 3 Mile Island type event where you break your fuel, but it doesn't get released into the atmosphere. 1 in a million per year is considered unacceptable. 1 in 10 million is considered high risk. 1 in 100 million is considered medium risk, and 1 in a billion is considered low risk. So even high risk isn't that unlikely for when looking at a more current reactor design. But so yeah, this is a very legitimate reason to decommission a nuclear power plant.
Over almost 3 decades of operation, they supplied enough electricity to power the entire country for 5 years. But after the Chernobyl disaster in 1986, the safety of early Soviet reactors became a big concern for the EU.
Rightfully so. And it's good that they're looking beyond just the RBMK boiling water reactor design. They're looking in other Soviet-era designs as well to fully evaluate the extent of condition and what improvements should be made, just like any engineer should after a major industry event has occurred.
The 2 units were switched off in 2006 and 2008. Decommissioning began in 2011, and by 2022, both reactors had been fully dismantled.
It's a long process. I'm less familiar with the standards over there, but again, within the US, a lot of surveys, a lot of dismantling, a lot of decommissioning. You need to take out a loan for that too, so it's very expensive, just like you would for building. It's essentially building things in reverse. The shame is this thing's not going to be producing electricity anymore, but I mean, if this is an older design, that safety standards are in a spot that you can't really retrofit. I mean, trying to retrofit a reactor containment building, for instance, that's you might be better off building a new one at that point, and certain types of machinery. Not sure if that's ever actually been done before, but you might just be better off building a new one.
As well as being paid for by Slovakia, 7 other countries have contributed to a support fund managed by the European Bank for...
Yes, I was going to say, decommissioning could be on the order of billions of dollars, comparable to building a new facility. So Seeing a coalition of countries get together, recognizing a safety concern, just like they did with the new safe confinement structure. That's this aircraft hangar-looking thing they slid on top of the Chernobyl sarcophagus. Yeah, it's good to see a group of people get together and help out, because this can get expensive.
For reconstruction and development. In total, the project is expected to cost around $1.3 billion and is being carried out by Slovakia's state-owned nuclear company. Now, decommissioning is necessary, but still, $1.3 billion isn't cheap. Thankfully for some, it's being funded by those governments, as money from the private sector is hard to come by in 2024.
Yeah, and it's difficult to get investors to go back behind something that isn't going to make them money in the future. It's even challenging to get investors to build a new one, because it's risky, investment risky, not nuclear safety risky. Just thought I'd make that clear. But and that's mainly just because of length of time to build. And once it's built, nuclear power plants can make quite a bit of money. I'll pin down a video in the comment below where I talk a lot more about that. But the short version is they make all their money quickly when they're operating, but investment risk is very high, so investors are going to demand a higher rate of return on investment, and the discount rate is so high over the course of how many years it takes to build one of these things. So it can be quite challenging, but something that isn't going to make money just decommissioning and shutting down. It'd be difficult to find private sector investors.
The good news is that we're not going to go over every single nut and bolt, because that would take some time. Instead, here's a summary of the key phases. First up was the removal of all the systems and buildings that were no longer needed to support the dismantling of the remaining equipment.
Okay, yeah, this is the oldest of the WWER design. It's also a small one, the 440 megawatts electric.
These included the turbines, the transformers, and the switchboards. At the same time, radioactive waste from the operation of the reactor was processed.
Note that, so on this diagram you see right here, yeah, the turbines, the transformers, switchboards, that exists in every power plant. Doesn't have to be nuclear. Pretty much the whole right side of the graph, so basically anything that is the non-nuclear part of the plant. The nuclear part of the plant is the reactor vessel that you see on the left in red, and the red pipe that turns into, they're using purple for some reason, for the cold leg after it boils the steam in the steam generator there. That's the only nuclear part of the plant. That coolant loop. That and the pressurizer, so the red bit going up to the pressurizer relief tank at the top. But that's the part that is mainly focused on in the context of radioactive surveys, the ones for decontaminating on the site. You do surveys on the non-nuclear part of the plant and the site area, the owner-controlled area, the land that the plant is built on, just to be absolutely sure, because especially if the intent is to release the land for use other than making a new nuclear power plant, you're going to want to ensure it's as if the plant wasn't even there.
More on that in a bit. Then, after a few years of this, work began on demolishing some of the structures that are more visible from the outside, like the cooling towers.
So note that the cooling towers are in the secondary, the non-nuclear part of the plant. A lot of people associate cooling towers with the reactors at the bottom of it or something like that. No. The cooling towers are all in the secondary part of the plant, and what's interesting is the plant I worked at didn't even have cooling towers. It had a massive reservoir instead, but all those cooling towers cool is the main condenser, the thing that condenses steam from the turbine.
They were 120 meters tall, and there were 4 of them, leaving behind 50,000 cubic meters of concrete, most of which was recycled.
Okay, so they're showing basically 2 sets I saw, so must have been 2 reactors, or they're just shutting down one of them for now. Is the other one a different type? That's not unheard of to have reactors of different design at the same site. I'll go back to Plant Vogel in the US, for instance. Vogel units 1 and 2 are an older design, and Vogel 3 and 4 are the brand new design. Well, I say brand new. The design isn't brand new, but the site itself is is brand new. It's very new for something that is actively built.
Or used to backfill the holes. Next, it was on to stage 2, which is where we find the really interesting stuff, starting with arguably the most critical component of all, the reactor pressure vessel.
Yep.
Inside this is where you'll find the coolant, followed by the core itself. Yes, that's by far the most radioactive section of the entire plant, where the atomic fission takes place.
So he says it's the most radioactive section. Yes, that's true while it's operating, because that's where the fissions are occurring. So in terms of dose fields, it's massive because of all of the neutrons. And neutron dose, compared to gamma radiation, that is, in terms of what it would do to the human body, is anywhere from 5 to 20 times more, depending on the speed of the neutrons. Most of it's going to be 5 times more for thermal neutrons, but for the fast neutrons, they're 20 times more dose. When it's shut down, and while you're decommissioning, you take all the fuel out. So at that point, the most radioactive area is going to be your spent fuel pool,
creating the heat that powers the whole system. A giant crane was installed to remove the vessel from the reactor shaft before it was placed into a special pool.
So that right there was a 250-ton crane. And one thing I will emphasize, this is a small one. For your 440 megawatts electric, that implies the core is about 1,200 megawatts thermal. Most pressurized water reactors, we're talking at least 3,000. The plant I worked at was over 3,800 megawatts thermal. So this is a little one.
This is so it could be taken apart remotely beneath the surface. Why? Well, because this part of the job involved segmenting highly radioactive waste, and doing that underwater meant workers were shielded from the radiation.
That's true. 23 feet of water will shield you, is more than enough to shield you from radiation. That's just the regulatory requirement in the US is 23 feet, even though dose rapidly goes down with every foot of water. About 5 to 8 centimeters cuts it in half. So workers at the top are more than safe.
But before these pools could be constructed, they had to make space for them, and that meant removing the steam generators, which required more heavy lifting. Believe it or not, these are where steam is produced that's used to turn the turbines, which then generate electricity. At Boanica, the generators were almost 12 meters long, weighing 145 tons.
Now that's an interesting shape for a steam generator, and again, these are a bit smaller than what I'm used to, but I'm used to them being like towers rather than sideways like this. The sideways ones I'm used to seeing are more like your feed water heaters in the secondary plant. But for a reactor this size, you could definitely get away with a container that's smaller. Here's one going into Vogel during construction.
And there were 6 of them on each reactor.
Okay, that makes sense. These are smaller because you're using more of them too. So that the plant I worked at that was much bigger had four reactor coolant loops, 4 steam generators. It's interesting seeing this many steam generators too, because usually the smaller ones only have 2 loops, at least to designs I'm more familiar with. But this is just another way to do it.
Each one had to be transported across the facility to the former turbine hall where they were fragmented, in other words, chopped up into pieces. Massive circular saws were needed to slice through the 140mm thick steel casings, and the more than...
These would need to be dose assessed as well for contaminants. There's a whole system called the steam generator blowdown system. What happens in these steam generators is... just like when you make tea, how when you boil away a bunch of water, there's little teeny tiny bits and pieces of minerals left in there because water is not 100% pure. And even though water is highly treated and purified within the secondary loop of the power plant, those mineral deposits need to be sucked out. And that's true in every type of nuclear plant. Now, what's unique to nuclear is it's possible to have primary to secondary leakage. That is to say, this orange and purple loop right here could have a teeny tiny hole in it, and you get your primary reactor coolant leaking into your steam generator. So the steam generator blowdown system has radiation detectors and demineralizers to filter out radioactive materials. And there's a whole procedure and process and an emergency procedure if it gets real bad for responding to a steam generator tube leak. The short version is you shut down the reactor, cool down, depressurize, and clean up the leak. That is also a reason why radiation monitoring is placed on the main steam lines as well, so you can see if a tube leak is occurring. It's a scenario I've seen run many, many times in the simulator.
Heat exchange tubes inside each one. But even with the reactors taken out, the shafts left behind also had to be broken down. That's because the concrete had become radioactive as well. The solution was to cut it into blocks, smash those blocks up with a hydraulic hammer, and send the rubble away for storage.
So concrete is great at absorbing neutron radiation. Hydrogenous material really slows down neutrons, and that's why the dose to the public from nuclear power plants is effectively zero. The disadvantages of concrete is, over time, through being in an intense neutron field, they can become activated by neutrons. Common elements within concrete, such as calcium-40, which is stable, can absorb a neutron to become calcium-41, which is radioactive. Also stable sodium-23, which is in trace amounts, but it can absorb a neutron and become sodium-24. And these bits and pieces of activated concrete need to be treated as radioactive waste. There could also be some surface contamination on the actual concrete after a long time of service, but this is one of the challenges and one of the reasons why it's...
Of the more than 800,000 tons of material that had to be sorted through, radioactive waste amounted to less than 1%. Albeit, that's still quite a lot when you do the maths.
It is.
So, how did they get rid of it? Well,
and a lot of it is, it's mainly just because of how you physically take something apart, and anything that is in contact with radioactive waste essentially becomes radioactive waste. For example, working dressed out in protective clothing in a radiological controlled area, and like the tip of your finger gets contaminated. Well, now your entire glove is contaminated. And if you inadvertently touched all portions of your protective clothing with just that little bit of radioactive something that was on your glove, well, all of your clothes need to be treated as radioactive waste and need to be taken care of. Now, granted, this is super low level, so essentially the treatment for it amounts to doing nuclear laundry, basically. But it's still, the amount of material can be much more. The amount of material that is treated as radioactive waste and contaminated is a lot more than the radioactive material that's just there. So that isn't to say 1% of a nuclear power plant by mass is radioactive. It's just what needs to be taken care of.
The answer was by sending it to the waste treatment centre that happens to be on the same site. Here, the waste is either separated, incinerated, compressed, or a combination of all three before it's packaged up and placed in containers. These are then sent off to a repository like the one at Mahortsay to the east, where...
So in here we're talking about low to intermediate level. Really intermediate level, because low can just decay on site and essentially doing nuclear laundry. High is the spent nuclear fuel that needs to be transitioned both to the pool and then to dry cast storage.
The waste is sealed in reinforced concrete boxes surrounded by multiple barriers. As well as storage facilities like this, there are also fuel processing plants across Europe which also have to be decommissioned when the time is right. France has one of the biggest at Le Hague, which is currently going through the process. What are the differences between this and a reactor site? Well, because there's a lot more radioactivity to deal with here, a lot of the cleanup is done remotely via operated vehicles and robotic equipment.
So the site that's designed to handle waste, where they have all this makes perfect sense, because now robotic vehicles, they do have them at nuclear power plants as well on certain things, but here you're talking about just dealing with waste in bulk. So they have access to a lot more of these type of drones at these type of sites.
Where humans are allowed inside, contamination is everywhere, including on the walls. To remove it, special resins are applied to the surfaces, which are then peeled off, bringing all the nasty stuff with them.
Yeah, some of these areas would include airborne hazards. Note that you don't have to wear a respirator just because an area is contaminated. It's specifically for airborne contaminants, and it's specifically where the dose from airborne contaminants would be higher than if you didn't wear a respirator. The situations where doses would be higher if you did wear a respirator is if the added bulk of the respirator makes the job take that much longer. So let's say a respirator cuts your dose in half, but it makes the job take 3 times longer. Well, you're better off not wearing a respirator. This is a common thing that's discussed in radiological briefs.
Back at Boanica, the plan is to have the entire site cleared so it can be reused for non-nuclear industrial activities by 2027. In the meantime, because it became the first plant worldwide to decommission a reactor of this type, its team of experts are now sharing their experiences. With countries from Armenia to Uzbekistan now planning similar projects, learning lessons from Slovakia could help give them a big head start. Overall, decommissioning is an immense job, one that's been made a lot harder by the fact that most reactors weren't built with this step in mind. But
that's true, and no one knows how to do it anymore either.
Things are starting to change. Some countries like Canada have now taken steps to ensure that any new facilities are designed with end of life as a priority instead of as an afterthought. Then there's the rise of small modular reactors, an advanced and compact new alternative to traditional reactors, which many consider to be the future of energy.
Not only do they last longer, they can be disposed of a lot easier just because they're smaller. There's no big, complex structures that you have to take apart piece by piece, which would lower both their construction time and their decommissioning time, that you can essentially just deal with the reactor in bulk. Now, they're a lot smaller, so you essentially need a 6-pack of reactors to produce a similar amount of electricity to a large nuclear power plant, but you could swap them one for one with each other. You could even decommission a big one and just bring in these small reactors and essentially make your new nuclear power plant right on top. That would be really cool.
They can be installed and crucially disassembled far more easily than the ones we've just seen, although they're yet to be fully adopted. So while decommissioning is a huge hassle at the moment, that might not be the case for much longer, which is just as well, because if nuclear is to become the major source of clean energy that many expect it to be, we're going to need to plan ahead.
That's true. Just like any good project manager, begin with the end in mind. I really like this video. Thank you very much for the recommendation. This was pretty good for a high-level overview. Thank you very much for watching. I'll see you next time.